So we're going to continue our discussion of aqueous solutions and look at the stoichiometry involved. So the first main concept is molarity. Okay, so to perform stoichiometric calculations involving solutions, we have to know a few things. First, we need to know the nature of the reaction. So what form do the chemicals take when they are dissolved? So soluble, insoluble, what's going to happen. Second thing we need to know is concentration. We need to know the amount of chemicals present in the solutions. And third, we need to know molarity. This relates to concentration. This kind of gives us a value for concentration. Molarity is a capital M. It's moles of solute per volume of solution in liters. And so we've got our capital M, moles of solute, or liter of solution, or moles per liter. So it's really important to be able to identify your solute and your solution so you can plug in the correct numbers. So let's look at an example. So calculate the molarity of a solution by dissolving 11.5 grams of solid NaOH in enough water to make 1.5 liters of solution. Okay, so we want molarity. Molarity is moles per liter. Well, this is grams, but we know that our NaOH is being dissolved, so that makes it the solute. And so since this is moles of solute per liter of solution, I know that I need grams to moles. So for this part, I need to do 11.5 grams to moles, and that will give me the top part. For the bottom part, I need liters of solution. Well, I've already got 1.5 liters of solution, so I don't have to do anything for the bottom. That's already set. So this is the only calculation step I need to do. So 11.5 grams of NaOH. Okay, well, in order to go from grams to moles, we need molar mass. So I've already done that, and it is approximately 39.998 grams, and that's per 1 mole. And so if I calculate that, I've already done that for you, it's 0.2875. So now I go up here, plug it into the top part, and that's my moles of solute, which is NaOH. And I'm going to divide that by my liters of solution. And if I divide those, I'm going to get 0.192. Okay, significant figures are also going to become important here. So go back up into the problem. I've got 3 significant figures. I want 3 in my answers. So 0.192, and this is molarity, so we can put a capital M. And that's of NaOH because that was our solute that was dissolved in water, the solvent. Okay, so let's talk a little bit more about concentration. So molarity describes the concentration of a solution before the solute dissolves. Okay, so we have this concentration of salt to put in water. So 1.5 molar NaCl solution means that 1.5 moles of solid NaCl were added to enough water to make 1 liter of solution. Okay, because 1.5 molar would be like 1.5 over 1. So because NaCl is an ion, that means it's going to completely dissociate, so the solution is going to contain 1.5 moles of the Na plus ions and 1.5 moles of the Cl minus ions. So let's look at how that relates to some other compounds. Okay, what if we had something like this, where we've got 2 nitrates? Okay, whereas before, NaCl breaks up into just Na plus and Cl minus, so it's kind of like 1 to 1 to 1. But here we've got our cobalt, cobalt 2 nitrate. Okay, that's going to break up into the cobalt ion, but this time we've got 2 of the NO3 ions. Okay, and that gives us a balanced equation. So what that means is that if I have 0.5 moles of cobalt 2 nitrate, because this is 1 to 1 with the cobalt, I have 0.5 moles or molarity of the cobalt, but because it's 1 to 2 with the nitrate, I need to take my molarity times 2, so that's actually going to give me 1 molar of the nitrate ions. Okay, so sometimes instead of finding molarity, we want to find moles or maybe even liters, and so all we have to do is rearrange that equation. So in order to get moles, we multiply the molarity by the volume and get the number of moles. Okay, so molarity is moles per liter. Multiply those liters on both sides, that gets them out the bottom. And then moles is molarity times liters. Okay, sometimes we also want our volume instead. And so in order to get liters, I'm going to divide by molarity. So that gives me moles per molarity. So all you're doing is rearranging the equation. Okay, so calculating the number of moles of Cl- ions in 1.75 liters of 1 times 10 to the negative third molar. Okay, so sometimes it's a good idea to write your information. Okay, and so we're looking for moles. Well, I know that molarity is equal to moles per liter. So if I want moles, I want liters at the bottom. That means I need to divide. So molarity times liters is going to give me moles. Okay, well, I have the molarity and I have the liters, so all I need to do is multiply them together. So 1 times 10 to the negative 3 molarity of zinc 2 chloride, and I'm going to multiply that by my volume, which is 1.75 liters of solution. And I've already multiplied those together. We should get 0.00. Yeah, actually, you're just moving the decimal 3 spots, right? Moles of ZnCl2. Now, that's not the end of the problem. They want to know moles of Cl- ions. Well, if we take our zinc 2 chloride and we break it apart, we're going to get our zinc ion. We're also going to get 2 chlorine ions. So just like before, take your molarity times 2, and that should give us 0.0035 moles of the Cl- ion. If we look at significant figures, our smallest is 2 with the 1 times 10 to the negative third. So our significant figures are good. Okay, let's see. Typical blood serum is about 0.14 molar NaCl. And I like to write my information just because it takes it out of the word problem, makes things a little easier to see. I'm looking for volume. Contains 1 milligram of NaCl. Well, when I see molarity, I should instantly think molarity equals moles per liter. I'm solving for volume, which is liters, so liters is equal to moles over molarity. Now, I've got the molarity. That's my 0.14. I need moles. Well, here I have milligrams, so I know I need to get this to moles in order to use it in my equation. So I've got 1 milligram of NaCl. To do molarity, we need to go to, moles, grams per mole, we need grams. So 1,000 milligrams is 1 gram. And I've done the molar mass for NaCl. It's 58.44 in 1 mole. And if we calculate that out, it's 1.71 times 10 to the negative fifth. And that's moles of NaCl. So now I can plug that into the top, and so my liters is going to equal my 1.71 times 10 to the negative fifth, and that's moles of NaCl, divided by my molarity, which is 0.14. And if I divide those two, I get 1.22 times 10 to the negative 4 liters. If I take a look at my significant figures, I have 2. So it's going to give me 1.2 times 10 to the negative 4 liters. Okay, so standard solutions are solutions whose concentration is accurately known. And so instead of, having a random molarity, we have a specific one, like 1 molar or 2 molar. We can use these standard solutions in titrations and in other chemical analysis, mainly dilutions, which we'll talk about in a minute. Okay, so to analyze the alcohol content of a certain wine, a chemist needs 1 liter of an aqueous 0.2 molar K2Cr2O7 solution. How much solid K2Cr2O7 must be weighed out to make this solution? So I'm looking for mass. Well, I have a molarity, so molarity equals moles per liter. I'm going to get mass from moles. So basically, I'm looking for moles first, then I'm going to mass. So molarity times liter equals moles. That's kind of the opposite of the problem that we just did. So my molarity is 0.200. My liters are 1. And so that gives me 0.200 moles of K2Cr2O7. Now I need to convert that to grams to get my final answer. I'm assuming grams. It doesn't say, but we'll go with that as our standard unit. Okay, and so that means I need the molar mass, and I've already figured that out. So in 1 mole, we've got 294.2 grams. And so if I multiply that out, that gives me 58.84 grams of K2Cr2O7. If I look at my significant figures, it looks like I have 3. And so I want my answer to be 58.8 grams of K2Cr2O7. Okay, so we said that standard solutions could be used in titrations and other chemical analyses, mainly dilution. So when we dilute something, we add water to a concentrated stock solution in order to get a desired molarity. Okay, and this is often used with concentrated acids and bases. In fact, in the chemical storeroom and lots of other places, you would buy a concentrated container of acid, small, okay, because you're going to dilute it usually, so you don't need a lot, and then you can make all different kinds of molarities of solutions from that one container, so it's much more economical. Okay, so the moles of solute before dilution is going to equal the moles of solute after. The moles aren't going to change, it's just the total volume and the amount of water is going to change. Because we're only adding water, and so this gives us a ratio. M1V1 is equal to M2V2. Where 1 represents the molarity and the volume of the original solution, and 2 represents the molarity and volume of your diluted solution, or what you're trying to go to. And remember, because molarity times volume equals moles, that amount is never going to change. You could do M1V1 or M2V2 and you get the same number of moles, which is why we can equal them together. A few pieces of equipment are usually used in dilution. First is a pipette. It accurately measures a given volume, usually small amounts. You can have volumetric, which if you fill it, it's a very certain volume. Or you can have measuring ones, which you can use a pipette bulb on the front here to get whatever measurement you want. We can also use volumetric flasks. So here, you would figure out how many liters you needed of your solution. You would add your amount of acid, and then you would fill it to this specific volume so that you would have your molarity. Okay, so let's try one. So what volume of a 16 molar sulfuric acid must be used to prepare 1.5 liters of a 0.1 molar? So this is what you want to get to. So this is our V2 is 1.5 liters. Really, it doesn't matter as long as you keep the concentration and the volume together. So V2 is 1.5 liters. M2 is 0.10 molar. We've got an M1 of 16 molar, and we're looking for V1. So I know M1 V1 equals M2 V2. And so if I'm solving for V1, I'm going to divide by M1. So we've got 0.10 molar times our 1.5 liters. And we're going to divide that by our M1, which is 16 molar. And I've already calculated this out, and we should get 0.09375 liters of our concentrated H2SO4, which makes sense because we're going from 16 molar to 0.1 molar. We're not going to be adding very much concentrated acid. It's a very small amount. Okay, let's look at our significant figures. We have 2, and so that gives us 0.094 liters of H2SO4.